The future of air travel will be realized by the dreamers of today, at the ticket counters of tomorrow. Engineers and travelers alike dream of sleek machines, tearing through the sky at twice the speed of sound. Others look toward mammoth double-deckers, flying villages with twice the room of today's jumbo jets. But tomorrow's air travel isn't just about speed and size. Beyond the horizon await outlandish new designs, aircraft flown and fixed by voice, facial expression, and brainwave. Highways in the sky conceived with the lofty goal of replacing the automobile. Wings of tomorrow which could forever change the way we think about where we are and where we're going. June 3rd, 1973, the highlight of the Paris Air Show, a showdown between two newcomers competing for a place in the future of air travel. On one side, the Anglo-French Concorde, on the other, a Russian Challenger, the Tupolev Tu-144. Such were the heady days when revolutionary aircraft promised to capture a global market yearning for supersonic travel. At stake was economic reward and national pride. The Concorde had flown earlier in the day, impressing the crowd with low passes and banking turns. Now it was the Russians' turn. Their flight plan was well rehearsed, but as they take to the sky, it's unclear exactly what precipitated the events that led to one of the greatest tragedies in air show history. After several hard banking turns, the Russians flew over the airfield, then roared skyward. Suddenly, the aircraft broke apart, plunging earthward in a ball of fire. The wreckage landed on a village, killing 8 people on the ground. Some historians blame a photographer's camera, which they say became lodged against the pilot's control stick. A more intriguing theory suggests that an unauthorized French Mirage fighter shadowed the Russian plane from above, taking pictures of its small canard winglets. As the Russians pulled skyward, they overstressed the plane, trying to avoid the Mirage. Some even claim that the French government did a deal with the Russians, exchanging sensitive information to keep them quiet. Whatever the case, the crash would haunt the Paris Air Show for years to come, and the ill-fated Tu-144 program disappeared behind the Iron Curtain. On a clear winter's day, a group of Russian designers and test pilots are reunited with an old friend. The aircraft that once promised to make Russia world leaders in supersonic travel sits quietly like a ghost from the past. But it's in looking to the future that a team of Russian and American scientists have awakened the mighty Tu-144. Their goal? Create a supersonic airliner, which will carry up to 300 passengers at speeds beyond Mach 2. A supersonic airliner currently makes daily hops across the Atlantic. The Concorde is the most recognized passenger plane in the world, but its success has been more aesthetic than financial. With only 100 available seats, the Concorde is limited to those willing to pay over $5,000 a ticket. Engineers at NASA and Boeing are sure of one thing: the next supersonic passenger plane needs to be bigger. From tip to tail, it will stretch almost the length of a football field. Its wing area will be greater than a 747 jumbo jet. The goal is to have enough space for over 300 passengers. But making supersonic travel affordable will take more than just adding seats. The shape and dimensions of the wing means that a supersonic jetliner needs to land with the nose high. Also, because of the narrow pencil shape, the cockpit sits well behind the nose. The Concorde overcomes this problem by drooping the nose downward during takeoff and landing, so the pilot can see. The system worked for Concorde, but it means added weight and complexity that today's engineers are hoping to do without. NASA wants to solve the problem by taking away the forward-looking window altogether, leaving windows only on either side of the cockpit. Helping the pilot see by taking away his window seems like a paradox, but designers are banking that future pilots will learn to fly using a television image of the world ahead. At the NASA Langley Research Center in Hampton, Virginia, this very idea is being explored. A SuperView simulator gives pilots the chance to try out a new way of flying. A large screen to the left represents the actual side window. The screen directly in front of the pilot is a simulated video image from a camera mounted on the aircraft's nose. The camera image includes a heads-up display telling the pilot altitude and bearing. Here, we're closing on a virtual runway at just over 400 feet. Landing a plane with a video screen will take some getting used to, but just for assurance, the pilot always has the window to his side.
The initial reaction we get from most pilots, particularly pilots my age, they can't believe that we're talking about putting a computer screen essentially in front of them and asking them to fly an airplane. But after they try it, they really have no problem with the idea.
Flying a windowless simulator is one thing, but landing a real plane without front windows is something else. So NASA took a Boeing 737, gutted it, and put in a windowless cockpit. Cameras mounted on the outside provided the view.
In the 737 flight test experiment, there were two display issues that we examined. For example, the location of the horizon in the side window probably has to match the location of the horizon in the forward display. If it doesn't, the pilot might lose situation awareness. When he's tracking aircraft moving from the side window across to the front display, the position wouldn't be continuous, and so he could get confused.
NASA flight tests were done in two parts. The first was to see how well the sensors picked up information, particularly other airplanes. The second part of the program involved actually flying and landing the 737 from the windowless cockpit.
That's why we pushed it to the end. We're hoping.
Check that at 30 and set 130.
The overall view of the world ahead came from a combination of digital video cameras, infrared images, and radar. Conventional television cameras have a resolution of about 20 pixels per degree, which is roughly 70/20 in terms of human vision. The camera system NASA hopes to develop will have a resolution of 60 pixels per degree, about the same as the human eye. But without windows, a pilot's most obvious concern is what happens if one of the systems goes down.
There's one camera system that provides the image for the pilot. There's another camera system that provides a different image for the co-pilot, so that if the pilot's display fails, the co-pilot still has an image. And then there's a third one that can be used to replace either the pilot's or the co-pilot's image. If all three of those were to fail, he would still have the conventional instruments that he has, an autopilot system that could land the airplane, and in the last backup mode, the side window.
At first glance, there's something very odd about this F-16 fighter. It has two different wings. This is because it's part of NASA's research into something called laminar flow. All airplanes suffer from the drag created by turbulent airflow over the wings. The turbulence is a natural result of the friction between the rushing air and the plane's surface. On a big passenger plane flying over Mach 2, the drag impacts range, efficiency, and fuel consumption. Engineers create smooth airflow or laminar flow by sucking air through tiny holes, each bored with a laser beam. Part of the left wing of NASA's F-16 is testing how this may work on future supersonic transports.
You have millions of holes that are drilled into the wing, and a suction device sucks on the boundary layer of the air that flies over the wing, and you get laminar flow. There is about a 10% reduction in the drag of the airplane, and that greatly reduces the fuel burn.
Of all the hurdles faced by Concorde's designers, few predicted that its greatest obstacle was environmental regulation. Supersonic engines produce unwanted nitrogen oxide, and worse yet, because these planes fly at such high altitudes, the exhaust is pumped directly into the stratosphere. The biggest challenges facing designers is making an engine that is efficient, friendly to the stratospheric ozone, and perhaps most of all, making it quiet. Future supersonic passenger planes will have to comply with strict noise regulations. To do this, engine designers are struggling with different ways to keep the noise down. But with 4 engines, each producing over 50,000 pounds of thrust, they have their work cut out for them. This is the model shop at NASA's Langley Research Center. This room is where the designs of tomorrow take shape, where concept becomes form. Here, thousands of man-hours are put into each model. Tolerances need to be exact. The goal is to keep the shape so true to scale that if the model was blown up to real size, it would be off less than 1,000th of an inch. This is important because as soon as they leave the shop, the models are repeatedly blasted in NASA's wind tunnels. The NASA Boeing high-speed civil transport is still evolving. New materials are being explored to withstand the punishment of supersonic flight. The plane needs to survive 60,000 hours of flight time at temperatures approaching 350 degrees. Engineers need to make the plane strong and durable while also keeping it light. In the years to come, different composites will be seared, frozen, beaten, and blasted. The only thing missing is flight tests.
The Russians are a unique resource because they developed the first supersonic transport. It's called the Tu-144.
Because of its size and wing shape, the Russian plane makes a more suitable candidate than the Concorde. In an unlikely agreement between NASA, Boeing, and the Tupolev Design Bureau, a Tu-144 was taken out of mothballs. Powerful new engines were borrowed from a long-range Blackjack bomber, and Russia's supersonic giant was brought back to life. Next, the passenger compartment was gutted, clearing the way for stacks of flight test equipment. The flight test program began in 1997. The modified aircraft was given the official designation Tu-144LL. Flight experiments were divided into 6 phases over the course of 32 flights. Sitting in the foreground is Tu-144 crew commander Sergei Borisov. Sergei is an unlikely choice to fly such a big plane. He used to fly fighters in the Red Air Force. Now he's at the forefront of a program that promises to pave the way for the next generation of supersonic travel. As the powerful Blackjack engines pin the flight crew to the back of their seats, it's clear why the Russians chose a fighter pilot to lead the mission.
I'd say the Tu-144 is eager to take to the sky. During takeoff, I only need to pull the stick back 2.5 inches.
The front gear leaves the ground at 220 miles an hour. The main gear liftoff at 250. In a plane with this kind of acceleration, there's little room for error.
You have to be very careful not to exceed 250 miles per hour on takeoff, because at this speed, the canards can break off. Also, the nose can break off because it's pointed downward 12 degrees.
The droop nose makes for a bumpy ride. Unsettled air rocks the plane, and the roar of the engines makes it impossible to talk without an intercom. As the nose straightens, Sergei and his crew disappear into the clouds. Within minutes, the Tu-144 climbs past 30,000 feet. Now the tone in the cockpit begins to change. Approaching the sound barrier, the chaotic sensation of takeoff settles into a peaceful ride.
When the nose straightens, everything quiets down. I don't hear the roar of the engines. And during the flight, it is remarkably quiet. When it reaches supersonic speeds, I can't feel anything. It's very smooth.
From the inside, the ride may be smooth, but what goes on outside tells a different story. Sensors attached to the wing to measure heat and airflow have been ripped off, taking the paint with them. Speeds approaching 1,600 miles per hour have taken a toll. The scars of flight serve to remind how difficult it is to build a passenger plane made to fly this fast every day.
During the first flight, the paint already began to flake off. We've started to repaint the plane, but because of the cold weather, we haven't had enough time. As you can see, even the NASA emblem is flaking off. Tupolev as well. We'll sort it out.
Engineers striving to create a supersonic transport have a long line of hurdles standing in their way. Every time a problem is solved, another creeps up behind it. Shaping the wing for high speeds makes it less stable during takeoff and landing. Building engines quieter also makes them heavier, and so on. But many believe that the desire to get places in half the time will overcome every challenge.
Supersonic flight is the future of passenger aviation. The experts say there's a limit to the size of current subsonic passenger aircraft, yet the number of flights per day continues to increase. Therefore, planes will need to go faster. I think people are ready to fly supersonic, and we will supply the plane to fill their needs.
If it works, the supersonic passenger plane of the future will carry travelers from LA to Tokyo in just 6 hours, at a 20% increase in airfare. For weary travelers, it sounds like a dream, but not everyone thinks the future of air travel is about speed. Airbus Industries in Toulouse, France, thinks that bigger is better. When the company wants to move wings from British factories to the main assembly plant in France, it turns to its outlandish cargo plane, the Super Transporter. Based on an American design called the Guppy, the Super Transporter is a sort of double-decker with a large cargo bay built into a standard passenger airliner. Airbus doesn't sell the plane commercially. It's used for company business only. But Airbus executives are betting that another double-decker will be the airliner of the future. In the spring of 1996, Airbus formed its large aircraft division with the goal of building the next generation's Super Jumbo. The design has been formally designated A3XX, and if all goes as planned, it will be the largest passenger aircraft ever to take to the sky. Representatives from 19 airlines are working with Airbus to make the double-decker giant a reality. Those involved are banking that the scale of such a plane will lower operating costs as much as 20% against today's big airliners. The first version of the A3XX is expected to carry over 550 passengers, but that's just the beginning. Airbus hopes that other variants will carry over 800 people. The plane will have 4 aisles, 2 on the main deck and 2 on the upper deck. Connecting them will be a large double staircase, reminiscent of an ocean liner or ferry. Despite its large capacity, Airbus designers claim that their plane will be able to land, park, unload, reload, and be back in the air within 90 minutes. But this may be easier said than done. Some analysts doubt that airports are ready to deal with such a big plane. In 1997, Boeing dropped plans for a super jumbo of their own. But with one eye on Europe's A3XX and another on the burgeoning growth in air travel, American industry isn't ruling out a bigger plane. One group, representing university students, industry, and NASA, have joined the search for the super jumbo of the future. The goal is to seat as many passengers as the A3XX, but the approach is entirely different.
To minimize drag, they wanted to minimize surface area. So they started with a sphere, which is the minimum surface area to enclose a fixed volume. And since you can't pack people very well into a sphere, they flattened it out into something like a hockey puck. Added wings, added engines, added control surfaces, and the result is the plane you see behind me.
The exact design took time to perfect, but engineers think they may have settled on the shape of things to come. It's called the blended wing body, and it may revolutionize the way we fly. The shadowy contours on the underbelly reveal how the passenger compartments blend into the wing. The design promises to carry twice the passengers as today's jumbo jets, while reducing emissions and fuel consumption by a third. The blended wing body will be just slower than current long-range airliners, but with the engines sitting in the back, it will also be quieter. The flying wing design isn't new. The haunting outline of the B-2 bomber has become a fixture at military air shows. The B-2 proved that flying wings could be flown safely, but a small crew of trained Air Force pilots, fully equipped with ejection seats and parachutes, is one thing. Convincing 800 people to step aboard a flying wing may be more difficult. But for proponents of the blended wing body, shape is everything. At roughly the same dimensions as current jumbo jets, it can handle twice the people. Dr. Robert McKinley explains.
The two models I'm holding are both the same scale. On my left is a 747-400, which is the largest passenger aircraft that can currently be purchased, and it carries about 421 passengers, depending on the airline and how they want to arrange it. On my right is the blended wing body. It carries 800 passengers, and you can see it's not significantly larger. The wingspan is about 25% more than a 747, but the takeoff weight of the blended wing body is almost the same as the 747-400. And so you're getting twice as many people for the same weight in about the same wingspan and significantly shorter.
The three passenger cabins will be divided into upper and lower decks. One cabin sits in the middle of the plane, and the other two sit on each side, blended into the wing. The luggage will sit further out on each wing. For the lucky few sitting in the front, a window will provide a view of the world ahead. But there is a problem. It's easier to pressurize a round aircraft than a flat one. In a cylinder, air pressure is equally spread about the interior walls. But air pressure wants to turn a flat plane back into a sphere. But ambitious minds at Stanford University, NASA, and Boeing see this as a design challenge rather than a showstopper. Before dealing with structures and cabin pressurization, the first step was to build a radio-controlled model. In mid-1997, industry execs and students alike gathered in the California desert for the first flight. 2 engines in the back powered the model. A camera was installed to give a bird's-eye view. One of the strengths of the flying wing is that it suffers less aerodynamic drag than conventional planes. This makes it more efficient and designers hope cheaper to fly. The result is lower ticket prices, but there's something else designers need to keep in mind. Most of the passengers will be sitting out on the wing, rather than over the center line like conventional airliners. This means that as the blended wing body banks right or left, passengers are going to spill their drinks. This problem makes safe air travel an issue, unless pilots come up with new ways of turning.
Current planes, all your people are in that tube and they're close to the middle of the plane, so when you bank, nobody moves very far. This aircraft, you've got people that are 60 feet off the center line, and when you bank, there's going to be a lot of motion there no matter how you do it. So we want to look at skidding flat turns or 1G maneuvers that nobody really notices because they're so gradual.
No matter how safe, efficient, or cheap the blended wing body becomes, its biggest problem will come down to looks. New airplanes fascinate people young and old, but it doesn't mean they're ready to jump aboard. Time will tell whether the blended wing body is too radical for weary travelers, or if it changes the way we think about flight. The future of air travel isn't just a choice between supersonic transports and lumbering giants. For short journeys, an entirely different kind of machine may step into the spotlight. It's called the tilt rotor. The most recognized incarnation of tilt rotor is the V-22 Osprey. The U.S. Marines, who often find themselves in tight situations, were quick to see the advantages of a machine that combines the qualities of helicopter and airplane. The Osprey is due to enter service with the U.S. military within the next several years, and when it does, it will mark the acceptance of an idea that has been a long time coming. Back in 1955, Bell Helicopter launched the world's first tilt rotor, the XV-3. The revolutionary machine proved the tilt rotor worked, but it didn't prove that it worked safely. 2 crashes showed that at the time, the concept was a little too far ahead of the technology. By 1973, Bell was ready to give the tilt rotor another chance. The XV-15 was built as a technology demonstrator to prove to a skeptical audience that such a machine had a place in military and civilian air transport. The test pilots landed on aircraft carriers, flew air-sea rescue missions, and made hops to oil rigs. The XV-15 showed that the tilt rotor could do jobs no other machine in the world could handle. But more importantly, it proved it could do it safely. The XV-15 was never meant to go into production, but without it, the V-22 Osprey program never would have happened. Lately, the Bell Boeing tilt rotor team has been flying their XV-15 in and out of city centers. The windows on the side aren't real. They've been painted on for effect. This is because they're showcasing the potential of their forthcoming civilian tilt rotor, the Bell Boeing 609. Big airliners need to land at airports miles from the city, but a tilt rotor can carry business travelers from city center to city center. In countries like Japan, the idea of building vast airports to handle increasing numbers of air travelers isn't popular. Europe is also running out of space. The last big European airport was built in Munich in 1989. Tilt rotor proponents argue that their machine can ease pressure on airport traffic by using small helicopter ports. Also, a machine taking off straight up is less offensive than a jetliner roaring skyward over miles of residential neighborhoods. The 609 tilt rotor will be about the size and shape of the Osprey, but unburdened by military gear, it will be a third of the weight. Its most immediate role will probably be seen in big business. For short hops, corporations will be able to move their executives cheaper and faster than standard business jets. Inside is room for 6 to 9 passengers. It may not be big, but for workers headed to an oil rig, corporate high rollers, or Coast Guard search and rescue crews, a machine that is part helicopter and part airplane may be the best of both worlds. Ever since the children of the 70s were introduced to a paddleball game they could play on their television, video games have become an American institution. First it was Pong, then Asteroids, Pac-Man, Frogger, and the rest is history. Today's technologies make yesterday's games seem almost quaint, but one thing hasn't changed: the love of video games among little kids and big kids alike. Companies like Evans and Sutherland have found a hungry market in the world of cyber fighters and virtual gliders. Company founders probably never dreamed of such a thing. The Utah-based company is in the business of flight simulators. Sitting in one of the domes are simulator instructor and trainee. Our pilot is on a landing approach to Innsbruck, Austria.
You're on 10-mile approach to the Innsbruck, Austria airport. A 10-mile approach.
The feeling of motion is incredible. You never know that you're just sitting still. It really feels like we're flying. Now this is the actual terrain of surrounding the Innsbruck airport?
That's correct. One of the things that civil airline simulators really need is to make sure that all the geography and the placement of the airport and all the features nearby are correct in size and shape and in placement.
There's nothing new about flight simulation, but lately the explosion in processing speed and digital compression is closing the gap between the real world and virtual reality. To save fuel and flight hours, airlines are leaning more toward virtual training. This means that flight simulators must portray the surroundings down to every last detail, like the flock of birds about to fly past the window.
Watch some of these pilots as they come out of a training session where they've lost an engine or they've had to do an approach down to minimum visibilities into a strange airport, and they come out of the cockpit with the same sweat on their face that the guys going in the real airplanes would.
For commercial pilots, the details of airport taxiways are as important as those in the air.
Now, if you were suggesting a particular wind speed and direction, would the windsock over there respond accordingly?
Oh yes, we coordinate the windsock direction and its speed. There's some airports where that's the only indication the pilot has.
The virtual airport at Innsbruck, Austria is alive with activity. The pilot needs to keep his eyes open for other planes. Next, he is faced with an exact image of the Innsbruck terminal, generated from photographs and digital imagery. Baggage handlers await the arriving plane. Food and fuel trucks move into position. Even the covering of the baggage carts flap in the wind. The goal is to completely immerse pilots within a virtual environment, so that when they approach an airport like Innsbruck for the first time, they will know they have been there before. Learning to get around in an airport is one thing, but doing it in poor weather is something else. In the past, the only way to gain experience in poor visibility was during adrenaline-filled moments, with hundreds of passengers sitting in the back. For years, simulators have attempted to recreate poor weather, but only recently have computers begun to approach the real thing.
Some of the things that we've been able to make breakthroughs recently are layered fog. It used to be that fog was just one value. It was the visibility, you could only see a certain distance no matter which direction you looked into, but that's not the way fog works in real life. If you look at fog from above, you can see that fog usually just lies in the low-lying areas of the terrain. And we wanted to simulate that, and we've been able to do that recently. We've also added things like snowstorms where the snowflakes actually come at you like when you drive your car through the snow is coming at you.
The hypnotizing barrage of millions of snowflakes is a familiar sensation for anyone who's driven through a winter storm. Generating the effect on a computer requires immense speed and memory, but perhaps one day such technology can be used to train car drivers. At times, it seems like there isn't any image computer programmers can't come up with. But this doesn't help when a pilot can't see anything at all. Some weather conditions, particularly at night, leave pilots blind to the world around them. This is especially hazardous as aircraft shuffle in and out of busy airports. But NASA is developing a system that could allow pilots to move freely in the murkiest surroundings. The program is called Taxiway Navigation and Situational Awareness, or TNASA. An exact map of the airport is stored in the computer's software. The cockpit's map and navigation system feeds information to the heads-up display in front of the pilot. A computer-generated row of green symbols creates a virtual taxiway in the darkness ahead. On the instrument panel is a map showing the entire airport. It displays all terminals and taxiways. Our plane is represented by a triangle. As other planes approach, the computer recognizes the logjam, then warns the pilot.
Traffic.
The computer decides right of way and assumes the role of traffic cop.
Cleared to cross. Cleared to cross.
NASA designers hope this system will lift the cloak of fog and darkness, helping to ease weather-related airline delays. But a system that creates a virtual image of a world we can't see may have uses outside aviation.
The head-up display, as we've designed it for taxiways, depicts the edges of the taxiway and the center line with this virtual symbology. Now, in theory, there's no reason why you couldn't take the same symbology, adapt it to put it on a head-up display on an automobile, so that the driver could then navigate on, say, a highway in conditions of heavy fog or a snowstorm or anything else that would reduce visibility considerably. So I think it has considerable potential for increasing the safety of the nation's highways.
While some dream of virtual interstates, others foresee highways in the sky. This is the goal of an ambitious program called Advanced General Aviation Transport Experiments, or AGAT. The idea is lofty to say the least, but if it works, flying an airplane could one day be as easy as driving a car.
If you stop and think about what makes an automobile relatively convenient and easy to use, intuitive to use actually, is that everything you need to know is presented to you out the window. Imagine now that we present in more intuitive graphical form information in the cockpit of these small airplanes, such as where am I on the map? Where is the traffic, for example, and I can call up traffic that will show me that information. Where is the weather? And be able to now depict graphically, intuitively, where the weather is. Where do I go next? And be able to now print on my computer screen my highway in the sky that now I will follow in the heads down or an out the window depiction one day of how to get to where I should go.
Highways in the sky have already made a debut. During the 1996 Summer Olympics, helicopters followed predetermined flight paths that mirrored the highways around Atlanta. The AGAT concept takes the next step. As an airplane departs the ground, the entire journey is laid out in front of the pilot. All the pilot needs to do is follow the yellow lines. The computer takes into account all other airplane traffic and ensures that no paths are crossed. Each pilot has his own highway in the sky. If the pilot runs into bad weather or just wants to change destination, the computer automatically selects a new flight path. AGAT proponents hope this will revolutionize the way we get around, while also being environmentally friendly. They mention that road construction would be eased if just 10% of the population traded in their car for an airplane. They also point out that few runways would need to be built because AGAT pilots could land at existing small airports throughout the country.
It's fascinating to look at an aviation map and study how many small airports there are literally dotting the countryside in comparison with how many large airports there are available that serve the scheduled air carriers. There are about 500 plus airports for scheduled air carrier service. There are over 18,000 landing facilities in the country. And so looking at a map to study that is really fascinating. Here's the Denver Stapleton, the old Stapleton Airport downtown here. And what you'll realize when you begin to study the map in a little bit of detail is that there's an airport here, there's one here, one here, one here, one here, one here, one here, up here.
Using small airplanes to get around has its advantages, but it's confined to the wealthy few who can afford a plane and all the expenses. NASA and its industry partners want to jumpstart private air travel by building a plane for the people. But the program has its skeptics. How much would it cost? How safe would it be? And what about the people we don't even trust behind the wheel of a car? Can we really trust them in the sky? In the years to come, many questions will need to be answered. Agate planners want to fundamentally change how we think about where we are and where we're going. But they also point out that even if a fifth of the people choose skyways over highways, we will have taken a giant leap forward. This Air Force maintenance officer looks like an extra in a science fiction adventure. But the headgear isn't some sort of cutting-edge system to track enemy soldiers through the darkness. It's meant to help him work on his airplane. A wearable computer on his belt has the entire aircraft maintenance book stored on disk. The mechanic flips through the manual, not with his hands, but with his face.
Check brakes for wear is my next step. Now I got to go outside and check the brake wear.
This is the Alternative Control Technology Division at the Air Force's Armstrong Laboratory in Dayton, Ohio. Dr. Grant McMillan oversees cutting-edge projects.
Place your tech manuals and your specifications when you're working on aircraft, you'll actually be using this wearable computer system that you see sitting here on the desk. But for the training process, we're going to use this desktop system because it's just a little bit more convenient to work with. Now what you'll be wearing in both cases is this head-mounted display, and this little miniature TV here shows you the same thing that you see on the screen on the laptop computer. And in this head-mounted display, you see we've got these 3 sensors, and what they do is they pick up the electrical activity from your facial muscle. Now you can go ahead and just open that up, you know, and then put it on your head and then get it.
The small monitor on the headgear is tied to the laptop computer. In the field, the computer would be worn on the belt. The goal here is to teach maintainers how to flip through computer files using facial expression alone.
Now let's go and actually train you to use the gestures that we're going to use for interacting with the computer. And there's actually 2. We're going to use an eyebrow lift, just a little flick of your eyebrows like that, to act like a mouse click or an enter. We're going to use a gentle closing of your jaw, gentle jaw clench to work like a tab. So when you're actually using the software, you'll tab from item to item by using the jaw clench, and then you'll select or confirm the items by using the eyebrow lift. So let's go ahead and practice that real briefly here. Clearly, some of the nearest term applications for this hands-free control are for people with a variety of physical disabilities, and this technology can provide that. Let's go ahead and try that. Just kind of a little flick of your eyebrows. Okay, good. And you see you heard the tone feedback, and you see right
Electrical muscle signals from the eyebrows send a distinct message to the computer, which it confirms with a red spike.
Okay, and what we're going to do with that is that will be used as if you were pressing the enter key on the computer. Okay, now let's try the jaw close. Okay, good. And you see you got a different feedback, a different tone. And you see how that signal looks a little different, that it's longer, stays above threshold for a longer period of time. Go ahead and try that a few times. And the way we'll use that in the maintenance software is that will work just as if you'd press the tab key.
Now, comfortable with facial gestures, it's time to take a tour of the software. Controlling the tab and enter key seems limited, but for reading a manual, it's all that's required.
Okay, now you've got that selected. Now you need to confirm it with the eyebrow lift. Okay, good. Okay, this is the first screen that you might see out in the field if you're doing this fire control radar equipment rack removal and reinstallation.
The idea behind hands-free controls is to let maintainers do their work without stopping what they're doing to refer to a book. But there are some pitfalls. If the mechanic strains over a stubborn bolt or drops something on his foot, the anguished facial expression might send an interesting message to the computer. The technology will take some perfecting, But already hands-free controls could help patients with spinal injuries use a computer, read, or change channels on their television. There are other uses for technologies that help people work without their hands. And in this laboratory, muscle-actuated control is just the beginning.
Another technology that we're looking at is the use of brain waves or electrical signals from the brain as a way to interact with computers and other sorts of systems. And for example, one of the responses that we've used is called the steady-state visual evoked response.
The goal here is the same as before. This time, all it takes is a headband, electrodes, and a little concentration.
Before, the controller involved EMG, which is muscle inputs from the face, forehead, jaw. This happens to do with brain waves. And so to do that, on this headband I have 3 electrodes that are actually at the back of the head, because what we do has to do with the visual evoked response.
If you've got a flickering area of a screen or flickering light that somebody's looking at, you actually drive the brain signals so that it reproduces to some extent that signal. So if you have a light flickering 10 times a second, included in your brain activity is an enhanced signal at 10 times per second.
As Dave looks at one of the flickering boxes, his brainwave is monitored on 3 levels. Brainwave frequency tells the computer which box he's looking at. This means when Dave wants to choose a box, he simply needs to look at it. Using brainwaves, Dave flips through the same program previously read with facial muscles. Now all commands are in the form of boxes, each flashing at a different rate per second. To check off that he's completed the first task, Dave concentrates on the box in the upper left corner. This activates forward and back commands. Now he concentrates on the forward box to take him to the next page. Through practice, Dave can get his computer to respond in just 2 seconds. But he's quick to point out the irony of brainwave control. Using your brain isn't something you think about, it's something you just do.
Too much introspection actually can be harmful. What you want to do is just, in your training, to become natural. It's sort of like in golf. The worst thing you can do to a golfer is ask where his left elbow is during his backswing, because he honestly doesn't know. It's just a pattern that he's learned. And this is much the same way. A trained individual will simply do the required activity without a whole lot of thought about it.
If brainwaves can be used to get around a computer, they can also be used to affect the movement of another object. This is the purpose of the alternative control technology flight simulator, which harnesses the power of brainwaves to move right or left. But this time it's less straightforward. Again, the subject uses visual evoked brain stimulation. The catch is, she needs to control her brainwave response to the flickering light.
The person has to go through a training process where we teach them to either enhance or to suppress this natural brain response to the flickering lights.
As the subject stares deeply into the flickering strobe, her brainwave responds in kind. Now she needs to take this brainwave frequency and somehow enhance it, sending a spike up through the center of an EEG waveform monitor. The simulator responds by rotating to the left. She'll maintain the enhanced brainwave response until the simulator goes as far as it can. Now, to get back, she'll need to somehow suppress her brain's response to the flickering light. Exactly how this happens is a mystery.
The way a person learns to do this is they go through a training procedure very much similar to biofeedback. So in the task display, there's a little indicator that tells them how big their brain's response to the flickering light is at that moment in time. And then they learn mental cognitive procedures. Usually people try imagery, they'll try thinking about things, they try relaxing or tensing themselves. and eventually they discover some method by which they can enhance or suppress that response. Usually they can't describe it very well after they're good at it, and it becomes, I just think that I want to go right, or I think that I want to go left. So it's an internal process that people are trained to do.
For some observers at the Alternative Control Lab, science is obscured by the supernatural. Their suspicions are bolstered when even PhDs don't have the answers to all the questions.
When we describe this to people, there's initially a little skepticism of whether this is associated with psychic phenomena, that sort of thing, and it's not at all. It really is just engineering and medical science and biomedical instrumentation, that sort of thing.
From walking to swinging a golf club, we all go about our daily lives without knowing exactly how. Perhaps one day quadriplegics will run their computers with brainwaves. Perhaps pilots will fly an airplane without even thinking about it.
The kinds of things we're doing here with EEG signals and with muscle electrical signals is not magic, it's not psychic, but there are details that we do not and perhaps never will understand.